Hello everyone, I'm Tony from Intel. Today I will give a talk on Foreseer, knowledge-driven acceleration of memory-bound matrix multiplications for large language model inference. This is the joint work with Yutao Xu. Inference of large language models, LLMs in short, is emerging. Many general matrix multiplications, GEMs in short, are memory-bound and critical to LLM inference. We start with the background on how GEMs are computed on GPUs and optimized with expensive offline tuning, which is not scalable. We then present Foreseer, a new analytic approach based on prior knowledge. After that, we evaluate the approach, demonstrating its effectiveness. Finally, we give the concluding remarks. LLM inference is autoregressive. A long prompt is input to a transformer model, generating the next token along with the KV activations for the context in the KV cache. The newly generated token is then fed back to the model, correlating with the history context in the KV cache, generating the new next token and augmenting the history. Such a process is repeatedly invoked, continuously generating new tokens until the stop criterion are satisfied. Therefore, in a relatively long output, decoding the next tokens, dominating the performance. In a transformer model, the input embedding layer translates the input token to a high-dimensional representation. The representation is then repeatedly transformed through many transformer blocks, and finally fed to an output layer for the output token probability. Each transformer block is composed of several layers of the self-attention module and the multi-layer perceptron module. 4 layers here are the GEMs and the element-wise processing afterward. Here, X is an M input activation vectors in dimension K. M depends on the batch size and bin search width in decoding. The input activations comes from the last layer's calculation, typically residing in the last level cache. W is the K by N weight matrix. Since the large language model is loaded layer by layer in inference, the weight matrix cannot fit into the cache and must come from the GPU memory. The output is M vectors in dimension N. Here we have M times N times K multiply accumulate operations, given N times K memory accesses, resulting in the arithmetic intensity of M. Due to the heavy occupancy of GPU memory capacity by the KV cache in linear with the batch size, and the stringent latency requiring small batch sizes, M is small and the GEMs are memory bound. Those memory bound GEMs then become critical to decoding next tokens. To calculate a GEM on GPU, we divide the output matrix into mutually exclusive tiles in a predefined shape. A tile is computed from the corresponding rows from X and the columns from W by a workgroup or NVIDIA's thread block. Within a compute unit or NVIDIA's streaming multiprocessor, threads in a workgroup are dispatched at the same time, sharing the L1 cache and the fast scratchpad memory. A tile is further divided into subtiles, also with a predefined shape by a smaller group of rows from X and columns from W. A subtile is computed by a subgroup or NVIDIA swap in lockstep. The computation is actually a reduction. The corresponding rows and columns are divided into blocks in a predefined stride. In each step, we perform the small block multiplications using the systolic array and reduce the results into the subtile. So far in the scheme, the software parallelism is capped by the number of subtiles. If it is not enough to saturate the hardware capability, we may slice the reduction into more subgroups, each performing partial reduction. The partial results are aggregated at the end. To optimize GEM of a given MNK shape on the target GPU hardware, we need to determine the right parameters of workgroup and subgroup shapes, the striding and slicing parameters. This is traditionally accomplished in an expensive search with extensive experiments, also known as tuning. The optimal parameters found offline is then encoded into the runtime for online inference. Such a process is difficult to scale for different weight matrices in different models, different batch size and bin width settings in inference, different model parallelism plans, and different GPU hardware. In short, the scaling is difficult. To confront the challenge, we propose Foreseer, a knowledge-driven approach without tuning. We leveraged prior knowledge as heuristics. For example, maintaining adequate pressure in fetching weights from GPU memory. A classical paper shows that sometimes in memory-intensive workloads on GPU, a lower concurrency leads to better performance, likely due to the contention on the on-chip interconnect, missing status holding registers, or bank conflict. This is to say that a too high concurrency may not be ideal. We also need to keep enough parallelism in terms of subgroups. We need to consider the load balance in work dispatching. Fetching the same weights from subgroups in a workgroup is rewarded for better memory efficiency. Slicing the reduction is penalized for the tail effect. We then evaluate different parameter choices with a coarse-grained analytic penalty function, but not relying on tuning or running on the target hardware. With that, Foreseer is able to generate the right parameters for gems on the fly. We take maintaining adequate memory access pressure as an example. Note that the input activation X comes from last level cache. Only weights comes from the GPU memory. In each step, for each subgroup, we access such a size of weight block. We then times it with the number of subgroups concurrently running, limited by the compute units. We then discount it with a factor of C from collaborative weight fetching. Here we can see that the two vertical subgroups actually fetch the same columns of weights. Since subgroups in a workgroup are dispatched at the same time, most likely they have a similar progress. Either the two subgroups fetch the same weights at the same time, resulting in memory collapsing, or the later fetching is served from the fast L1 cache fetched earlier, so memory requests gets discounted. Now we are able to calculate the memory access pressure for a certain parameter choice. We prefer keeping the pressure within a range, which may be platform specific. We use a simple method to determine the range. We tune for 4 gem shapes in GPT-J for optimal parameter choices, and then derive the range from the pressure of the 4 optimal choices. With that, we now define the analytic indicators to penalize the case falling out of the range. Here we use logarithm to smooth out extreme values. The indicators are associated with penalties. We believe that maintaining the lower bound of memory access concurrency is more important than keeping below the upper bound, so we apply a higher penalty for the former. We introduce 6 indicators ordered by importance. For example, we evaluated the extent of maintaining minimum number of concurrent subgroups similarly. We have a Boolean indicator to prefer dispatching all the work in one round only to avoid the load imbalance tail effect. We reward the collaborative weight fetching for the improved memory efficiency. And we also consider the tail effect for slicing the reduction. Now we assign the penalty and the rewards for the indicators in a decaying series, approximately in a factor of 2. Note that the positive reward here is for collaborative weight fetching. Finally, the score comes from a weighted combination. Instead of predicting the performance accurately, here we prefer a simple and explainable design to discriminate good enough choices from bad ones. We implement Foreseer as a patch to Intel extension for PyTorch, IPEX in short. IPEX 2.1 provides the optimized LLM inference engine for Intel Max GPUs. GEMS with post-processing are implemented with the Intel Xe templates for linear algebra. For selected models with selected batch sizes and bin width, GEMS are tuned with a table to keep the choices identified. For unseen shapes, it falls back to Intel 1DNN, the vendor library for GEMS. In Foreseer, we intercept the shape identification in the IPEX optimization path, replace with the Foreseer policy to generate the GEM parameter choice, and then route the choice back to the GEM implementation infrastructure. To evaluate Foreseer, we use the high-end Intel GPUs. Max 1550 is the IPEX optimization target, but the newer Max 1100 is less powerful with a different compute memory capability ratio. We use the Llama 2 models with different sizes, Code Llama, OPT, and Bloom, some using tensor parallelism due to the GPU memory limitation. We do not use GPTJ since it is used in determining the platform-specific constants. We perform both micro benchmarks with memory-bound GEMS and end-to-end next token decoding. To simulate memory-bound GEMS in the micro benchmark, we prepare a set of matrices in the same dimension and use them in a round-robin manner to avoid the catch effect. In the micro benchmark, we first look at the geomean for various arithmetic intensities. Here, the 100% is defined by the best known performance tuned with exhaustive search in a large space. We tried different baselines. For example, a compute-bound parameter choice. The choice maximized the parallelism only on the shape. We also considered the choice performing the best on average for GPTJ for this specific arithmetic intensity. We used two recent 1DN versions, the vendor library for GEMS. The earlier version has not been likely optimized for memory-bound cases, but the later version has. We see that Foreseer outperforms the other baselines on average, exceeding 90% of the best-known performance. On Max 1100, Foreseer performs similarly, but even better. On average, Foreseer reaches more than 90% of the best-known performance in GEM micro benchmarks. We also look into individual GEM shapes, for example, certain arithmetic intensity on different platforms. Foreseer performs stably in all those cases. Next, we show the experimental results for end-to-end next token generation. The 100% baseline here is the case that we always fall back to the earlier 1DN version in IPEX. IPEX 2.1 combines tuning for selected batch size in the LLMs on Max 1550 and falls back to the improved 1DN version otherwise. We see that on average, Foreseer significantly outperforms the baseline. Its performance is at least comparable with and quite often exceeds the optimized vendor inference engine, IPEX 2.1. We then dive into different inference settings on a model on Max 1100. Comparing with IPEX tuned on a different platform, Foreseer is more effective in transferring to the different GPU hardware, providing consistent performance improvement and demonstrating its effectiveness. To conclude, we have proposed a new approach, Foreseer, to accelerate memory-bound GEMS for LLM inference. Foreseer does not require tuning for each gem shape and GPU hardware combination, but foresees the good performance with heuristics and analytic evaluation. Experimental results indicate that it performs well on Intel GPUs. Due to the hardware resource limitation, we leave evaluating Foreseer on NVIDIA and AMD GPUs as the future work. Since NVIDIA provides CUDAs for customized gem and post-processing implementation, we hope that transferring Foreseer to NVIDIA GPUs is relatively trivial. Given the contact information and the artifact location, this is the end of my talk. Any questions or comments are welcome. Thank you.